this video, we are going to explain about using TensorFlow library in implementing the GANs method on MNIST image dataset. The basic idea of GANs is that you have two models, a generative model, which is called the generator, and a discriminative model, or the discriminator. The discriminative model has a task of determining whether a given image looks natural, and by natural I mean an image from the dataset, or it looks like it has been artificially created, or a fake image. This is basically a binary classifier that will take the form of a normal convolutional neural network, or CNN. The task of the generator is to create natural-looking images that are similar to the original data distribution. In order to use GANs, we need to have the following: real training images, which is the MNIST dataset here in this example, a generator network that takes in a random noise vector and produces a synthetic image, a discriminator network, which is a convolutional neural network, or CNN, that learns to distinguish between real and synthetic images. You can think of it as just a binary classifier, in which 1 is for the real image and 0 is for the fake image. An optimization procedure that jointly updates both networks through SGD, or stochastic gradient descent. This is the tricky part, as we need to train the generator network to fool the discriminator network. And we need to have TensorFlow, which is our choice of deep learning. So let's get started. First, let's start with our imports. In this part of the code, we have imported TensorFlow, NumPy, Random, and Matplotlib libraries that we would be using in the next parts. Now we have to import our MNIST images. To do this, we'll call a TensorFlow function called readDatasets, as you can see here in this line. This loads in the 55,000 training examples in the MNIST database. The MNIST variable we created above actually contains both the images and their labels. Let's just isolate the image for now. There will be 55,000 images, and each of them will be of size 28 times 28. So here we have isolated the training images from the labels of the dataset that we have. We have got the shape of the training that we have. You can see that the shape is 55,000 and 55,000 samples and 784 features, which is 28 times 28. Now let's look at what a random image might look like. Here you can see one of the samples of the training set. Now it's time to design the architecture of the discriminator. Thus, we define a CNN classifier function that takes in an image of size 28 times 28 as input. The architecture of the deep convolutional neural network, or CNN, that we consider has 4 layers. As you can see, we have defined 4 different layers of convolutional neural networks and pooling layers. The first layer is a convolutional layer with a 5 times 5 kernel, 1 input channel, and 8 output channels, or output depth. And it is initialized by a normal distribution. Here you can see the first layer architecture. So the weight kernel is 5 times 5. It is initialized by a normal distribution. The number of the input channels is 1, and the number of the output channels is set to 8. The bias is initialized with 0 value, as you can see here in this line. We will use the function tf.nn.conv2d through our code in order to get the convolution. It is actually the TensorFlow's function for a common convolution. It takes in 4 different arguments. The first one is the input volume. The next argument is the filter or weight matrix. Finally, you can also change the stride and padding of the convolution. You can see the function that I was talking about here. The input, the filter, the weight function, the strides, and the padding. Those 2 values, I mean the striding and the padding, affect the dimensions of the output volume. Then the ReLU activation function is applied to the result of the convolution, as you can see here. The pooling is done by using tf.nn.averagePool function from TensorFlow library. The kernel for the pooling is set to 2 times 2, and the result would be the average of the input values lying in this kernel. You can see it here, the pooling. The kernel size is set to 2 times 2. And the stride is 2 times 2 as well. The other layers would be the fully connected layers. The first fully connected layer has 7 units, and since we have 2 dimensions, the total number of the weights that are defined here would be 7 times 7 times the number of the outputs, which is equal to 16. These are the parts that I'm talking about. So I skipped the explanation of the second neural network, convolutional neural network that we have here, because it is as the same as the first one. Nothing has changed. Just the input channels and the output channels has changed, and the number of the neurons that we have in this layer is different from the first one. The first one had 8 units, and this one has 16 units. Everything else is the same. So I was explaining the fully connected layer here. The number of the outputs of this fully connected layer is set to 32, and the ReLU activation function is applied on the multiplication of the flattened output of the previous layer, and the weights which is then added to this bias, as you can see here. The last fully connected layer will have 32 inputs and 1 output, which determines whether an input is a fake image, whether the output is equal to 0, or it's the actual or real one, which is equal to 1. This structure simply shows the binary classification using convolutional neural network. So this is the last layer, which is a fully connected layer. It has 32 inputs and only 1 output, which would be 1 or 0 for 2 classes. You can see the output here. Now that we have our discriminator defined, let's take a look at the generator module. You can think of the generator as being a kind of a reverse convolutional neural network. With CNNs, or convolutional neural networks, the goal is to transform a 2- or 3-dimensional matrix of pixel values into a single probability. A generator, however, seeks to take a d-dimensional noise vector and upsample it to become for example, 28 times 28 image here in this example. This upsampling is done through a convolutional transpose, which is also called deconvolution layer. ReLUs and batch norm are then used to stabilize the outputs of each layer. So this part of the code shows the architecture of the generator that we have written here. The structure of the generator is very similar to the structure of the discriminator, except that we're calling the convolution transpose method instead of the convolution one. The convolution transpose plus ReLU plus batch norm pipeline is repeated 4 times here in this part of the code, so that the output volume grows larger and larger until we would get a 28 times 28 image. The number of the filters of the first layer of the generator is set to 64 and the color dimension is set to 1 since the images are grayscale. So this is the first deconvolution layer that we have. The number of the inputs is equal to 64. The color dimension is equal to 1. And the output size would be equal to 28 because we want a 28 times 28 image at the end. Actually, we want the generator to generate fake images which look like real images of this size, 28 times 28. And we want to start with a noise vector and get matrices after each deconvolution layer, and we would like to have gradual increase in the size of the matrices in order to get the 28 times 28 matrix at the end, or image at the end. So these determine the gradual increase in the size of the output image. The output size is 28. Since we want to slowly upscale the image, we generate different upsampling factors, which, as I said, are called S2, S4, S8, and S16, and apply the ReLU function on the vectorized input. Each layer would be upscaling by a specific factor like S2, S4, S8, and S16. The first layer gets a 2 times 2 noise image and upsamples that to a 3 times 3 image. It uses a 5 times 5 kernel initialized with normal values, and the bias term is also randomly generated. Then the transpose convolution is applied with strides of size 2 times 2. To increase the stability of a neural network, batch normalization normalizes the output of a previous activation layer by subtracting the batch mean and dividing by the batch standard deviation. So that is the reason why we apply the batch norm to the previous result. After the ReLU activation function is applied, and the output would be of the size batch size times 3 times 3 times 246, in which 256 is 4 times the input size, which was equal to 64. You can see this part of the code, which shows the structure of the first layer that I was talking about. The kernel has the size 5 times 5. And you can see that we have applied the transpose of the convolution here and added the biases and used the batch norm here. After that, we have applied the ReLU activation function. The same method is used for the second layer, which has the output size of batch size times 6 times 6 times twice the size of the input, which would be 128. The output of the third layer is equal to batch size times 12 times 12 times 64. The fourth layer also follows the same structure, but the output would be computed as the tangent hyperbolic of the transpose conv 2D result, which would be in the range between -1 and +1. This shows the structure of the fourth deconvolution layer. The third one was just like the other two ones above, so we skip the explanation of that one. So the output of the fourth layer would be between -1 and +1. The output size of this last layer would be batch size times 28 times 28 times 1, which is equal to the size of the image that we have in the training set, because remember we were looking for images of size 28 times 28. Now that we have defined the discriminator and the generator functions, let's train the generator with noises. Because, as I said, the generator receives the noise in the beginning and tries to get or generate the fake images that look like the training images that we have in the data set. Since we changed our batch size from 1 to 16, we need to reset our TensorFlow graph. In order to start the evaluation of the tensors, we call a session and determine the shape of the inputs to the generator and discriminator by using the placeholder that you can see here in these lines. As you can see here, we have a placeholder for X and a placeholder for Z. So this X needs a placeholder for input images to the discriminator, and Z needs a placeholder for input noise vectors to the generator. The loss function is a little bit more complex than that of the traditional convolutional neural network classifiers, because in the traditional CNN classifiers, a simple MSE or mean square root error or the hinge loss would do the trick. But here it's a little bit more complex. If you think back to the introduction, again, can be thought of as a zero-sum min-max game. The generator is constantly improving to produce more and more realistic images, while the discriminator is trying to get better and better at distinguishing between real and generated images. This means that we need to formulate loss functions that affect both networks, the generator and the discriminator. So we need two loss functions. dx will hold discriminator prediction probabilities for the real MNIST images. gz holds the generated images, and dg will hold discriminator prediction probabilities for generated images. You can see them here. We want the generator network to create images that will fool the discriminator. The generator wants the discriminator to output a 1 or positive sample. Therefore, we want to compute the loss between the DG and label of 1. This can be done through the tf.nn.sigmoid cross entropy with logits function. This means that the cross entropy loss will be taken between the two arguments. The with logis component means that the function will operate on unscaled values. Basically, this means that instead of using a softmax function to squish the output activations to probability values from 0 to 1, we simply return the unscaled value of the matrix multiplication. This is where we have used this tf.nn.sigmoid cross entropy with logits. The reduce mean function just takes the mean value of all of the components in the matrix returned by the cross entropy function. This is just a way of reducing the loss to a single scalar value instead of a vector or a matrix, as you can see here in these lines. And the loss would be the summation of the two losses that we have. Now let's think about the discriminator's point of view. Its goal is to just get the correct labels. Output 1 for each MNIST digit and 0 for the generated ones. We'd like to compute the loss between dx and the correct label of 1, as well as the loss between dg and the correct label of 0. Once we have our two loss functions, d loss and g loss, we need to define our optimizer. Keep in mind that the optimizer for the generator network needs to only update the generator's weights, not those of the discriminator. In order to make this distinction, we need to create two lists, one with the discriminator's weight and one with the generator's weights. This is where naming all of your TensorFlow variables can come in handy. As you can see, we have used the d dash or d underline and g underline in order to find the values that we have already named. So g underline determines all of the weight values that we have for the generator, and the d dash or d underline will show us all of the weight values for the discriminator. So we can call all of them or put them in these tensors. D underline vars, G underline vars. Next, we'll specify our two optimizers. In today's era of deep learning, ADAM seems to be the best SGD or stochastic gradient descent optimizer, as it utilizes adaptive learning rates and momentum. We call ADAM's minimize function and also specify the variables that we wanted to update. As you can see here, the minimizers are called. So the training loop is as following. During every iteration out of 1000 total iterations that we have specified in the beginning of the code, there will be two updates being made, one to the discriminator and one to the generator. For the generator update, we'll feed in a random z vector to the generator and pass that output to the discriminator to obtain a probability score. This is the dg variable we specified earlier. As we remember from our loss function, the cross entropy loss gets minimized and only the generator's weights and biases get updated. We'll do the same for the discriminator update. We'll be taking a batch of images from the MNIST variable we created at the beginning of the program. These will serve as the positive examples, while the images in the previous code that we had, the previous section of the code, are the negative ones. Now that the training of both the generator and the discriminator is complete, we can take a look at one of the sample images that the generator has made. remember that the generator has to give us fake images that are pretty similar to the real images or actual images that we have in the dataset. Here you can see what the generator can actually make from noisy data, because remember we gave it noisy data in the beginning in order to get a 28 times 28 picture, which is quite similar to the data set that we have, the digit data set that we have. It only receives noise and is able to give us an image which is kind of similar to the training data set. We can increase the number of the iterations in order to have more accurate picture at the end, image at the end. Also, there are some other hyperparameters that we can play with in order to get more and more accurate images at the end.